Pearl paper. And the speaker is Benjamin Chung from Northeastern University.
Just a quick shout out to the brief interruption. I just wonder, is Dmitry Mordvinov here? Hi, so you're giving the next talk. Are you okay to sign a speaker release form for the presentation?
Is this on? Yes, okay, good. So this work is focused on describing and proving correct the subtyping algorithm that Julia uses to decide subtyping between unions and tuples. So this algorithm is something that probably isn't new to Julia, though we're not exactly sure about that. We've been told that this algorithm that I'm going to describe has existed as tribal knowledge in the subtyping world for some time, but we haven't found a specific example of it. If you know of one, we'd be really excited to hear about it. So, before I talk about subtyping, I first need to talk about types, or more specifically, the values that give rise to our types. So in our system, we were just worried about thinking about here integers and booleans. We then can combine these integers and booleans into tuples, and can combine tuples and integers and booleans into further nested structures. This gives rise to sort of infinite hierarchy of potential values. We can then abstract over these values into types. We can form tuples of all integers and all booleans, or tuples of all integers and all booleans. But what if we wanted to abstract a little bit further? What if we wanted to have multiple different sort of kinds of value inhabit one type? One way that we could do that is we could introduce union types into our language. So what we're saying here is that we have this tuple whose first element is a union, and whose first element is an integer, and whose second element could be either an integer or a boolean. In this way, both of these values, one of which has a boolean for its second argument, and the other has an integer for its second argument, can inhabit the same type. We could equivalently write this type using unions by just explicitly writing out all of the tuples that describe the original values we were putting into it. These two types should be exactly equivalent. They should describe the exact same set of values, and therefore we would expect them to be equal to each other. Along with this notion of equality, we could also define the notion of inequality, or less than equals in our setting. So for example, we would expect to have the tuple of integer to be a subtype of our larger union, because our larger union is the union of two things, one of which is our integer type. Now, we would like to practically be able to use this less than equals, or this subtyping relation, which means we would like to be able to decide it. One way that we could do that is we could use a sort of syntax-directed set of subtyping rules. So if we see a union on the left-hand side of our subtyping relation, we could say the thing on the right-hand side has to be a supertype of both things in the union. If we see a union on the right-hand side of our subtype relation, then then we get to choose which element of the union the thing on the left needs to be a subtype of. And finally, if we see a tuple, we can just recurse down into the tuple and all's good. So what's the problem? This seems right. This seems like it would logically make sense. But if we go back to these types that I had said earlier should be exactly equivalent because they would seem to describe the same set of values, we find that the syntax-directed algorithm is insufficient to be able to decide that this subtyping relationship holds. More particularly, it will say that this subtyping relationship doesn't hold. Why? The reason why is because it's syntax-directed, it will see this union on the right-hand side and then be forced to make a choice. It will have to go either left or right in this union immediately before we're able to pick which direction we go on the inner union on the left. Consequently, we end up asking whether integer union boolean is a subtype of an integer or whether integer union boolean is a subtype of boolean, both of which are false. And therefore, the syntax-directed algorithm cannot conclude the seemingly correct subtyping relation. So how is this solved traditionally? The answer is something called normalization. The motivation for normalization arises by observing that this problem arose because the structures on the two sides of our subtyping relation were not exactly the same. the structures are sort of misleading us into making the wrong choices. So if we make sure that the structures, if the layout of the unions is exactly the same on both sides, all is well. So what we do in this normalization approach is we take the inner union on the left-hand side of the subtyping judgment and expand that out into a disjunctive normal form of union-free type terms connected by unions. So if we do this normalization procedure to these two types, then what we end up with is exactly the same two types on the sides of the subtyping judgment. And our simple syntax-directed relation is able to decide that these have a subtyping relation between them. Note at this point that it would be sufficient to be able to decide subtyping to simply compare the sets of union-free type terms that we see on both sides of the subtyping relation. Because they're in this sort of disjunctive normal form, all we have to do is establish that there's a subset relation between the union-free type terms that we see on the left and the union-free type terms that we see on the right. That's enough to decide subtyping. So this seems all well and good, and I will say that this is an exactly correct algorithm. It is logically, it works. It will decide subtyping that with distributive unions. But is this actually practical? So we can start to see some hints of a problem if we examine this relatively simple type. This type has just 3 unions in it, but its normal form has 8 separate union-free type terms in it. This is not such a problem, but it's hinting at the exponential space and time complexity of this normalization algorithm. We will generate an exponentially large number of union-free type terms by exploring all of the choices throughout these types. And this is okay for this type, but is it okay in actual implementation? Can we use this in a real language? Well, in Julia uses subtyping as a fundamental part of its dynamic semantics. It's constantly calling subtyping to figure out what it's going to do next. And because Julia programmers like writing types, they've also written types with lots and lots of unions. We've actually seen a union that has a function that has a signature with a tuple of 15 union types in it, expanding to more than 32,000 union-free type terms. If we were to try to normalize this, it would end really badly. So in order to be able to make Julia efficient, we need some sort of algorithm that's at least able to solve the space problem, if not the time problem. We need to be able to do better than exponential space if we want to have a practical subtyping algorithm for a language like Julia. Now, the approach that I'm going to describe and the approach that Julia uses is based on iteration. Instead of computing all of these union-free type terms up front, like we would do with normalization, we instead compute them one at a time. And as long as we don't have to remember any of the others, we don't have to store them. So how can we do this? So to explain how we're going to iterate over these types, I need to change the representation that we use to look at these type terms. Instead of writing our types as this sort of flat string form, I'm instead going to draw them as a tree where the tuples and unions are nodes and our base types are leaves. Then, at each of these unions, we have the ability to make a choice as to which way we're going to go. If we assign a choice to each of these unions, to all of the unions that we need in a sense, then what we'll end up with is a union-free type term, because we've made a choice as to which direction we've gone at all of the unions, and therefore all of the unions go away, union-free type term. So if we make the left choice, which was sort of chosen arbitrarily as an initial state to start from, we end up with the union-free type term consisting of the tuple of Boolean integer for this initial type. We can then start iterating over this type. And the way that we do this is we take this fully left state and shift it more towards the right. If we turn our rightmost left choice into a right, then we end up with a union-free type term of Boolean. And if we do this in a sort of reverse in-order traversal, where we try to push everything more right, we will end up converting the bottommost left into a right choice and reinitializing the other branch of the tuple to left because we're iterating in this recursive left to right fashion. Consequently, if we continue this pattern, we end up in our terminal state. We end up in this fully right state where we've managed to iterate all the way across our type, and we end up producing the union-free type term Boolean. Now, in this process, what we've been able to do is we've been able to explore all of the union-free type terms that we would have gotten out of normalization, but we haven't had to explicitly normalize. We've been able to generate each of them one at a time. And moreover, we've been able to generate each of them from just making a single choice at each union. As long as we don't have to look at any of the other union-free type terms, we can implement this algorithm by just remembering all of the choices we made for each of the unions, and there's linearly many unions. So as long as we can implement this without remembering any other of the union-free type terms, we can decide subtyping in linear space. We still will take exponential time because we have to explore all of the union-free type terms, but linear space improvement. So to explain how our subtyping algorithm actually works, I'm going to dive a little bit into the details of our cock proof as I explain how we use this to decide subtyping. So to start off with, I need to define what subtyping actually means for us. So we use a denotational, in order to define subtyping, we use the denotation of a type containing unions as the set of union-free type terms that that type would create from normalization. So if we were to, so the denotation of a primitive type, an integer or a Boolean in our sense, is just the singleton set containing itself. The denotation of a union of two types is the set union of the union-free type terms that we would get from either side of the union. And the denotation of a tuple is the Cartesian product of the union-free type terms that we would get out of that tuple. We then define subtyping as if these denotations are in a subset relationship, then subtyping holds. And then we can define a decidable normalization relation in a straightforward way by defining a norm function that just computes this denotation, and then we decide the subset relationship in the straightforward way. What we're going to do with this iterative algorithm is establish the same subset relationship, but do it by establishing a mapping between the things on the left to the things on the right. If we can find a mapping from every element on the left to some element on the right, then we know that the subset relationship holds. So, as an example of this, we're going to try to establish a subtype relationship between the type T and the type T prime. We're going to start iterating by iterating over the type T, which starts at the state integer, which starts pointing to the union-free type term, integer, integer. Then we initialize the right-hand side iterator, also at integer, integer, which happens to match. We have found an equivalent type, and we can move on. We then step the left-hand side iterator forward because we've already found a match for the previous element, and start searching through the right-hand side type again. The first element isn't a match, so we continue onwards. Second isn't either, but the third is, and we have found a match for the second union-free type term in the left-hand side. Consequently, we have been able to match every single union-free type term in the left-hand side to some union-free type term on the right-hand side, and therefore a subset relationship exists between the denotations of these types. Therefore, subtyping would hold between these two types, and we haven't had to ever store all of these union-free type terms in memory at once. If we were to say that this final union-free type term in the type T prime didn't exist, this one that we needed to match the second element in the iteration over T, then we have in a sense found some certificate, some evidence that subtyping doesn't hold. We have found that there exists some union-free type term in T that does not exist in T prime, and therefore the subset relationship does not hold, and the subtype relationship does not hold as a consequence of that. Now, our implementation in cock was a little bit funny. So what we set out to try to decide was whether this sort of fundamental for all exists, or whether this subtype relationship actually held. What we wanted to do was we actually wanted to have a cock program that you could actually execute. And in order to do this, you need to be able to you need to convince cock that your recurrence will eventually end. In order to do that, you need to have some sort of structure that's always decreasing, and our iterators are not obviously always decreasing. To construct some always decreasing construct, we needed to introduce this iternum system, which numbers each of the iterator states based on the number of remaining transitions you can take from the current state. So in the final state, iternum equals 0. And then, as our induction step, what we need to show is that if the property that we're interested in looking for holds for the succeeding case, then it holds for the preceding case. If we can show that our predicate holds for both of these, if we can check in both of these cases, then with our induction principle, we're able to effectively iterate over all of the states in the iterator and decide whether our property of interest holds or not. In order to define these properties that we're actually looking for, we need to sort of incrementalize the original property that we were looking for. So in order to do this, I'm going to introduce this pipe I sub t thing. What this describes is the set of union-free type terms that you can reach from the current iterator state I when iterating over the type t. So if I was to ask how many union-free type terms remain from the initial state of the iterator over t, then it's just the same set of union-free type terms that you would get out of normalization. Then, ignoring the failure case, if you're interested in what happens with this, if the types aren't subtyped, you can check out our paper, then we can define the predicates that we're interested in for the left-hand side, which is, again, just the incrementalized version of what we're searching for. We're saying that we must be able to map every single element in the remainder of the iterator over t to some element in the iterator over t prime, starting from the beginning. On the right-hand side, we have the incrementalized version of the property we were trying to show there, which is saying that there must exist a match for the element that we're searching for that we got from the left-hand side somewhere on the iterator on the right-hand side. If we then apply this induction principle to our property, we end up finding that it holds, we end up being able to decide that it holds for any given iterator. We're able to run it over the iterator for any given type. We can then initialize this with the initial state. And if you remember, I said that the denotation of the iterator starting from the initial state over the type t is equivalent to the set of union-free type terms we would get out of normalization. As a result of that, we're able to show that this for all exists relationship holds, and then that subset holds, and then that subtyping holds as a result of that. So I've described a bit about I've described Julia's algorithm for deciding subtyping between unions and tuples, and described a bit about the core of how we proved it correct. However, we didn't prove a lot of Julia's actual type system, and the algorithm that Julia uses to decide subtyping for it. In particular, I only talked about how we dealt with primitive types and not the arbitrary user-defined type systems you can have in real Julia code. Moreover, Julia goes further and lets you write bounded existential type variables, which always adds some excitement to a type system. And I also didn't cover invariant constructors in Julia, which are a feature of Julia that actually forces them to use this iterative algorithm rather than normalization, because you can't define a correct normal form if you have invariant constructors. If you're interested in details of that, you can check out our paper. Finally, Julia has the diagonal rule, which is an exciting case where you can have invariants come out of simply multiple appearances of the same covariant type variable, which can be challenging to figure out when applies. If you're interested in trying out our algorithm, it's available as part of our artifact as a web application. You can try it here. You can enter in your own arbitrary types and see how it works. OK, thank you very much, and I'd be happy to take questions.
Thanks, Benjamin, for your clear presentation. So we have time for a few questions. Sophia?
So thank you for a very interesting and surprising result also. I was wondering, can you generalize your result? Can you say, so far you have dealt with essentially with two combinators, tuple and union, but there are others, intersections and so on. So could you generalize it and say, as long as the first combinator has these and these properties, and the second combinator has these and these properties, I can develop the algorithm and so on?
We absolutely suspect so. We haven't proved it. We don't have a formal proof of it, but this algorithm has apparently been in use in other systems, though we don't know exactly what. And Julia uses this exact algorithm over a much more complicated type system than the one that we described here. We just, again, haven't fully formalized it and proven it correct.
Hi. How does your algorithm handle projections? Do you add a rule for projecting over unions?
We do not. Let's talk offline. The details of how it would deal with that may be a bit complex.
Sounds good. Thank you.
Okay, thank you. Let's thank Benjamin.